Charles produces shows in medium-sized towns. The fraction of the population that purchase tickets in similar towns is approximated reasonably well by 25 p raised to the negative 5, as long as price is at least $2. His constant per ticket cost is $4. Letting n represent population and ignoring capacity constraints, Charles' profit function is blank. So we need to solve for profit. Well, remember that profit is total revenue minus total cost. Another form we can write this in is price minus marginal cost times quantity. So let's plug in what we have. We know marginal cost is $4, and we know that quantity is the population size, in this case n, times the fraction of the population that actually purchased, in this case 25p raised to the negative 5. So to get it in a form like we see it on the test, we need to distribute through q. We do that, we distribute through n times 25 times p raised to the negative 5, and we get this. When we times p to the negative 5 times p, that gives us p to the negative 4. Because when you multiply two constants that have, because p by itself has an exponent of 1, we just don't see it. We add their exponent. So we have p to the negative 5 plus 1. This gives us p to the negative 4. And when we multiply through, 4 times 25 gives us that negative n times 100 p to the negative 5. So now that we have our profit function, let's look at the second question. It says, if population is 125,000 and the venue holds up to 625 customers, what price maximizes profit? Well, again, here's our profit function. Let's plug in our n of 125,000. We get this as our new profit function. We're now ready to take the derivative of this with respect to p. So we do that. Let's talk about this derivative. The first part, 3.125 million times p raised to the negative 4, when we take the derivative of that, we multiply the 3.125 million by negative 4, giving us negative 12.5 million. And now we have to subtract 1 from our exponent. So we went from p to the negative 4 minus 1 to p to the negative 5. Now the second component, we do basically the same thing. Negative 12.5 million times negative 5 gives us a positive 62.5 million, and the p to the negative 5 becomes p to the negative 6 because we subtract 1 from the exponent. We know we're going to set this equal to 0. Now here's a trick we can do in math. As long as we do something to one side of the equation, as long as we do it to both sides of the equation, we haven't changed the equation. It's a legal math move. So to make our life easier, we're going to multiply everything through by p raised to the positive 6. 0 times p raised to the positive 6 is just 0. But this helps because take a look at our first function on the right, negative 12.5 million times p raised to the negative 5. When that's multiplied by p raised to the positive 6, we're going to add those exponents. Negative 5 plus 6 gives us a positive 1, so we're just going to have p. The second part, 62.5 million, p raised to the negative 6 times p raised to the positive 6. Again, we're going to add those exponents, but negative 6 plus 6 gives us 0. So any number raised to the 0 is 1. So we can rewrite this as negative 12.5 million p plus 62.5 million. Now we're ready to solve. We add 12.5 million p to each side, and we divide through by 12.5 million, and we find that our optimal price is $5.